Thank you very much, Sylvie, for this lovely introduction. And thank you, Phil, Sylvie, and the TC209 for giving me this wonderful opportunity to be presenting today. I am super honored and delighted to be talking about my research this morning about shared anchor pi response to multi-directional lateral cyclic loading. Before we delve into the technical aspects of this talk, let's remind ourselves where we've been, where we are, and where we're going in terms of expansion of offshore wind. So I've summarized here all the continents that are represented here at ISFOG, with the progression of offshore wind in ISFOG units, that is every 5 years. And as you can see, we've made tremendous efforts to bring offshore wind to commercial viability. And this has been possible through amazing progress in a lot of domains, and one of them is foundation design. Moving forward, we need to continue doing this, but moving to floating wind. And although the share of floating wind might be limited in the next decade, it is really important, and this is why. On this map, I have put in dark blue all the water depths that are greater than 80 meters. 80 meters because this is the limit after which bottom fixed structure are no longer commercially viable. And this is a map of the wind speed across the world. And this is what happened when you superimpose the both of them. Basically, anything that is in dark green on this map is untapped offshore wind potential. And we can only access those water if we develop floating wind. Floating wind could generate 11 times the global electricity demand that's projected for 2040. However, at the moment, it is hindered by very high cost, but also infrastructure that's currently not present, like grid, manufacturing, storage, and installation. There's a big need for us to understand how to make floating wind cost-effective, and this includes foundation design. There are 4 types of main floaters that are currently possible for floating wind, from which are derived hundreds of prototypes. Let's review them together. The first one is stabilized in place through mooring in tension, called the tension leg platform. The following 2 are buoyancy stabilized, and the final one is stabilized through ballast and is called the spar buoy. Apart from the first one, all the other one can be moored into place through taut, semi-taut, and catenary mooring system. In this talk, I am going to be focusing on catenary mooring system because it is the simplest from the point of view of the anchor in terms of loading. But later on, of course, research will expand this to other types of mooring lines. If you have 1 turbine, you may have 3 to 9 lines mooring this into the ground. Now, if you have 100 turbines into your farm, that's 300 to 900 anchors, and that is costly. One way to reduce the cost from mooring is to develop shared anchoring. Shared anchoring can reduce the cost of offshore wind, and initial studies show that this can be up to 16%, but this is still work in progress, and maybe we can save more. In addition, it can minimize the seabed footprint, installation time, and environmental impact. However, using shared anchor also generates new loading onto the anchor, and in particular, multi-directional cyclic loading, which can alter the capacity and the stiffness, and therefore the ultimate limit state design, but also the accumulated displacement over time, which is called ratcheting. And this could increase the risk of cascading failure of the anchor, and therefore compromise the integrity of the wind farm. Therefore, we really need to understand how to develop shared anchoring in the future. There are several types of anchors that can be used to moor catenary mooring line and other types of mooring lines, and I've summarized them here on this slide. They are usually categorized in 2 types of anchors, traditional and developmental. Traditional because we've had some experience in oil and gas, and there are some design guidelines for them. Developmental because that does not yet exist. To be able to devise a shared anchor, we need an anchor that's symmetrical so that loading can be applied in any direction. I'm going to talk about the anchor pile because it is the simplest design, but it's also versatile, adapted for a wide range of soil conditions, and is the basis of understanding for us to continue developing a lot of the developmental anchors. However, despite piles being quite established and having good design guidelines, we do not yet understand its response to multidirectional cyclic loads, and we need to understand this better in order to be able to use them for shared anchoring. In addition, understanding multidirectional loading on piles can also further optimize the design of our monopiles. Monopiles are particularly susceptible to misalignment caused by wind and wave, and therefore need to be designed for static cyclic load misalignment, which is very similar to what we see for anchor piles. And this is an animation that shows the misalignment of the wind on the left-hand side and wave on the right-hand side on a range of wind farms across the globe. To be able to understand multidirectional loading on piles further, we need to do a range of experimental testing in order to have a database that evidences the key mechanisms driving the pile response to multidirectional cyclic loading and static cyclic load misalignment. This database can then be used to develop numerical models that are computationally efficient to model long-term cyclic loading. And as you will see in my talk, this is not very obvious. But if we manage to do that, we'll then be able to enhance our design capacities and provide simplified design guidelines for industry practice. So it's quite important that we're able to do that. In this presentation, I will present 3 different projects to which I participated in that tackle this issue. 2 projects that are experimental, one on the geotechnical centrifuge at the UGE, which was part of the Mutant project, and one at the large-scale 1G testing facility in Darmstadt that was part of the University Grenoble Alpes-led project, GeoLab SAMWT. I will then consolidate those 2 experimental databases into an impetus for the development of a new model that I've been developing with Anna Paré from NGI called CLAP for cyclic loading analysis of piles. And if you want to learn more about all of these projects, there are several talks throughout this conference by Ricardo Zabata, Rami Chaloub, and Anna Paré, and I invite you to go and watch them. Starting off with the Mutant project. Mutant is a France Énergie Marine-led project that's run through the French Agency of Research, ANR, and that has involved 5 work packages in order to understand the commercial viability of shared anchors. It includes load analysis, geotechnical design, and cost analysis. And if you're interested in the output of this project, you can flash this QR code, and it will take you right through to the webinar that presents all the final results. In a nutshell, the geotechnical design involves some centrifuge testing that was performed at the University Gustave Eiffel by Ricardo Zabata, myself, and Mathieu Blanc, and for which our wonderful technical team has developed a bespoke experimental equipment that can apply multidirectional cyclic loading onto a pile, and that you can see on the left-hand side over there. The tests were performed at 83.3 G, run fast, and for this, I have a zoom on the instrumented pile that we've used and on which we're applying the load at the bottom. The system is made of 3 electrical actuators that are connected to a dynamo and extensible cables and apply loading at 120 degrees from each other, very similar to the configuration of the shared anchoring I've shown earlier. We've also used this very same setup on other foundation type and other loading, including moment and vertical load, and there will be 2 flash presentations by Shizumi Feobu and Cristian Soriano Camelo later on today to present this. Let's have a look at the tests that we were able to perform with this test campaign. We've done a range of tests, but I'm going to be focusing on one, which is called the cross test and corresponds to cyclic static load misalignment and is a typical test in offshore wind because it corresponds to wind and wave load misalignment. Before I delve into those details, let's understand the representation I'm going to be using, which is on the rows on the left-hand side on this graph. If I were to do unidirectional cyclic loading and I were to represent this on a 2D plane, I would be cycling along the line such as this, and this would be corresponding to the horizontal load that's appearing on the right-hand side diagram. If now I'm doing multidirectional cyclic loading in the cross shape, I'm first going to be pushing the pile straight up. Then I'm going to be maintaining this load, and then I'm going to be applying two-way cyclic loading in this manner. And this is a cross test. When I'm doing this cross test, this is a displacement that I'm obtaining also in the 2D space. First, I'm pushing the pile, and I'm maintaining the load. And then I'm doing two-way cyclic loading. What do we observe on this graph? First, there's a strong reduction in the in the displacement spread angle, that is the footprint of the displacement on the ground, compared to the load that I'm applying onto the pile. But most importantly, we have a very significant accumulation of displacement in the direction of principal load that would not happen during two-way cyclic loading without any maintained load. And that's very important to design because that could be detrimental to our initial design. To see this clearer, the best is to project this onto what I call the maintained load axis, which is this axis in blue on this diagram. And if I do that, and I first start by looking at the unidirectional cyclic loading, these are the results. I'm going to pass them in light color so that I can then compare them directly to my multidirectional cyclic load, the cross test that's shown here in bright color. And what you can see is that the accumulation that we got from the cross test is much larger than what we would have gotten from the unidirectional cyclic test. So that could be a concern moving forward. Let's compare this to other test results from the SAM-WT project. The GeoLab SAM-WT project is a European project that was led by OEM Genk in Grenoble, who I'm kindly going to use here as a unit of scale to see the size of the pile. We're not doing centrifuge testing anymore. And the tests were performed in Darmstadt through the help of Rami Chaloup, who was the researcher on this project. The pile is a 2-meter depth pile, and it's connected to two actuators that are 90 degrees angle from each other and can apply any load sequence that we wished onto the pile. And we've done a cross test as well as part of this project. It's slightly different from the Mutank one in the fact that it has a different load angle, but what I see on the results on the right-hand side, which represents a displacement, is very similar to what we've seen in Mutank. We have a reduction in the spread angle of the displacement and an accumulation of permanent deformation in the direction of maintained load. And this is what we got in Mutank side by side, and you can see that those two key mechanisms really pop. What happens if we project now onto the direction of maintained load? The left-hand side shows you the results that we've already seen for Mutank, and the right-hand side show you the results for the SAM-WT project. Very similar curves. This is what happened when we superimpose with a unidirectional cyclic test. But the philosophy for SAM-WT is slightly different from the one that we had in Mutank, as in Mutank we compared with similar cyclic load to the maintained load, while in SAM-WT we aim for the mean load of the unidirectional cyclic test. And what you can see is that the residual displacement is fairly similar in this case. Now, this is a very strong result. Don't go and use this result to do your design using unidirectional cyclic loading. We need to verify this first, but this gives a philosophy of the test that we need to do moving forward. A philosophy of the test moving forwards, well, when you start doing multidirectional cyclic loading, so many load case scenarios come to mind as to what we should be doing. And then you add pile geometry and soil conditions, and this becomes really, really mad. So we need to have robust finite element analysis or other numerical ways to compute the response of the piles, to do large benchmark, to then be able to produce design guidelines for industry practice. Now, we've tried to model the Mutank tests using the hyperplastic constitutive model in 3D FE, and this takes a few weeks. We haven't tried the SAM-WT, but it's going to take a while. So we need simplified way to do this faster. And this is where CLAP comes from, because with CLAP, I can do the Mutank test in a few minutes and the SAM-WT in a few hours, and this is not yet optimized, so I'm pretty convinced that I can bring this further down. I don't have the time to present the CLAP model in details, but Anna will do that later tomorrow. CLAP stands for Cyclic Loading Analysis of Piles and is being developed by myself and Anna Paré. The principles are very easy. Anna participated to the development of Red Wind back in 2019, which can model full coupling between horizontal load and moment loads, but it's not able to capture the accumulation of permanent deformation under cyclic loading. At the same time, I was participating to the development of HARM, which is a model that can model long-term cyclic loading, but cannot do full coupling. The idea of CLAP is to bring them together into a unified method that can do multi-directional cyclic loading. And I don't have the time to show you how this is implemented, but I can show you how, once calibrated, I can model the tests for the Mutank project and the SAM-WT project, and this is what I get. And this compares fairly well with the two key mechanisms that we've been seeing for multidirectional cyclic loading: the reduction of spread angle and the accumulation of permanent deformation in the direction of maintained load are both here. If I project onto the maintained load axis, these are the results I get. This is the experimental result that you've seen before, and this is the results from CLAP. Pretty good. This is encouraging because that means that we now have a tool that compares well with experimental data and can enhance our benchmark capabilities to then devise simplified design methods for industry practice. The challenges here is that this is a very new model, so I haven't really looked into calibration yet, and ideally we will want to be able to do calibration based on CPT data and cyclic DSS. But this is to come. However, this can model ratcheting in any direction that we want, and we can also do reload following cyclic loading and assess changes in stiffness and capacity. So this is pretty good for design purposes. In conclusion, shared anchoring could reduce the cost of mooring and minimize seabed footprint, installation time, and environmental impact of floating wind. The challenges that come with it is that anchors are now subjected to strong multidirectional cyclic loads that can alter capacity, stiffness, and also accumulate permanent deformation that could increase the risk of cascading failures and compromise the integrity of the wind farm. There therefore needs to be further understanding and rigorous modeling of this phenomenon. Mutank and SAM-WT are two experimental projects that aimed at understanding this further, and they both demonstrate that the pile response to static cyclic load misalignment is characterized by a significant accumulation of permanent deformation in the direction of maintained load and a reduction in deformation foot spring angle compared with the load angle. The comparison with unidirectional cyclic loading is still uncertain and requires further work, but both test campaigns give you an idea of the philosophy of testing that we might want to be doing. The CLAP model enables to capture those key mechanisms that we've observed experimentally and enhances the capacities to benchmark and devise simplified design model for industry practice, providing that further work is done on calibration. Finally, none of this work happens without a strong research and technical team behind them, and I want to thank all of my colleagues who've participated in those projects and helped me participate in them. For the Mutank project, Mathieu Blanc for all the very interesting discussions we've had together, Ricardo Zabata for all the work, Tanguy Kokyo for the project lead, and the technical team for a wonderful model in the centrifuge. For the GeoLab SAM-WT project, Oriane Zheng for inviting me to take part in this project, Rami Chalou for all the work, and all the team at the Technical University of Darmstadt for welcoming us and providing wonderful models at large scale, and it's very difficult to put them together. And finally, Anna Paré for all of her enthusiasm in embarking on this modeling journey with me. And a final thanks to Luc Torel for all of his support during the preparation of this Bright Spark lecture. Thank you very much. If you want to know more about those topics, you can read further through the papers of this conference, but also by scanning the QR codes that are over there. Thank you.